Welcome back, my dear students. Now it's the final problem in the final part of the BJT lecture. In part 3, we deal with the introduction to an AC circuit based on a BJT. In part number 4, we solve together an example for a common emitter, a BJT amplifier. Now we will terminate this lecture by the final example, which is a common emitter BJT amplifier with a common emitter resistance, with an emitter resistance. This will be the final example in this lecture. As we did for the first lecture, for the previous part, we will start with plotting the circuit given in the problem. So now we have our BJT again. Again, it's an NBN BJT because we have the arrow is directed toward the emitter. This is the emitter, this is the base, this is the collector. For the emitter, now in the previous example, if you remember, we have a directly connected current source to the emitter, and then we have a negative VEE. Now we have a resistance. This resistance is called RE. And then we have our current source. And finally, we have, this is current I, and finally we have the negative VEE. And again, like the previous example, the current source is short circuited by a capacitor, so this current source will not act in the AC analysis because this capacitor will tend to a short circuit. Now, regarding the base, typically the same like the previous example. We have an RP resistance here connected to the ground. Then we have the coupling capacitor. And then finally we have an R sweep and the free sweep. So it's identically the same like the previous example. Again, for the collector, the same configuration. We have a coupling capacitor. We have the R load. And now this is the V out. And we have the RC resistance, the collector resistance connected to it. So this is the full configuration for our transistor. Now we have to find the three main unknowns: the input resistance, the output resistance, and also what's called the gate. For the input resistance, in this example, you will have to find two types of input resistance. First, you will find the input resistance here at this stage, and also you will find the input resistance here at this stage. So once before and once after the resistance RV. So we will calculate two input resistance. For the output resistance, the arrow is indicating here. So these arrows are given in the examples. And of course, for the gain, this is the V output over V input. This is the relation we are seeking for. In the previous example, my dear students, we solved the problem using the BI model, the small circuit BI model for a BJT. In this example, we are going to use another model, which is typically the same, which is the T model. Let's first remember what is the T model. The T model is like that. So this is the emitter terminal. This is a resistance called RE. Sorry, it's R small e. And this is alpha times IE. And this is the base terminal. And of course, this is the collector terminal. So as you can see, it's a current-dependent current source, alpha times IE. You have the base here, and you have the RE, which is a small resistance here. Of course, this alpha E is typically the same like GM times VP. So it is typically the same, GM like VP, which is the same as alpha. So this is the configuration we have, and this RE is equal to alpha over GL. Okay, so now we have this configuration. What we are going to do is to replace the BJT transistor here by this model. Let's start doing this task. So let's first replot the T model. So we have a current source. It's called alpha times IE. You know from the previous lectures that alpha is equals to beta over beta plus 1. And here you have the resistance, which is RE. And now this is the emitter, this is the base, and this is the collector. Let's now start to connect the three terminals based on the circuit. Again, let's start with the collector. With the emitter. Now the emitter is connected to a resistance which is R capital E, and then we have this capacitor which make a short circuit with the ground. So now all this will be short circuit. We will not have a current source. We will not have the VEE, which is disabled, of course. And then we have emitter connected to a resistance RE and then to the ground. So it will look like that. RE, and then we have a ground. What about the base? For the base, first you have a resistance called RB connected to the ground. Then the capacitor is a short circuit. Then you have the R swing and you have the input, which is V swing. So first we have this resistance, RB, and then we have R swing, and we have the voltage here, which is V swing. Okay. Then what about the collector? For the collector, first we have the resistance RC. This is connected to VCC. Now VCC is disabled. It's become a ground, so RC connected to ground. And also we have RL connected to the ground. So here we have RC connected to the ground, and then RL connected to the ground. So this is typically the model of our circuit. Use the T model of the circuit. This is a small signal model of our amplifier using the T model. Okay. Now let's start to calculate the input resistance, the input impedance, or the input resistance, or the output resistance. If you remember in the problem, I mentioned that we have two types of input resistance. We have an input resistance in this stage and another input resistance here. Let's make it 1 and 2. So let's start first with 1. In 1, we will exclude RB. We don't have RB. So we just determine the input resistance here. So I'm here and I'm in this stage, if you can recognize it, and I need to calculate this resistance. So the resistance at this point, we can say that I will call it R in 1, for example. Any resistance is voltage over current. So the resistance at this stage is simply the voltage drop here, which is VP, because this is the voltage on the base, that's right, over the current drop here, which is IP. So if I have VP and RP, I have the voltage. Okay, so this VP, you can call it V input or whatever, over IP. Okay, how can we get this relation? So let's first start to think. We know that IB equals IC over beta. This is a common relation as far as this transistor is working in the active mode. And as I said in the previous section, whenever it's an AC circuit, I will say to you in the question, please assume that your transistor is working in the active mode. So using this equation, you can say that RE is equals to VP times beta over IC. That's true. Okay. What about IC? Okay, IC is this. What is IC? IC is alpha over IE, sorry, alpha times IE. So Rin equals to VP times beta over alpha times IE. And then, what about alpha? Alpha equals beta over beta plus 1. So Re equals to VB times beta over beta times IE over beta plus 1. Okay, then here beta can go with beta, and then we have VP over IE times beta plus 1. So now we reach this relation. Sorry. Now we reach the relation that the Rin is equals to VP over IE over beta plus 1. But what is the value of VP over IE? Please recognize VP is the voltage of this point, and IE is the current flowing in this branch. This is the emitter branch, and VP is the voltage here in this point. So the voltage here over the current here is simply the resistance, the equivalent resistance here, which is the summation of R small e and R capital E. So now Rin number 1 is equals to R capital E plus R small e times beta plus 1. Simple. Okay. Now we determine Rin number 1, which is here. This is number 1. What about Rin number 2? The input resistance here. Oh yeah, it's simply the same like we calculate in number 1, parallel to RB. So the equivalent resistance from here parallel to RB. So you can say that Rin number 2 is simply equals to RB parallel to beta plus 1 times Re plus Re. So this is the second input resistance. Now, what about the output resistance? Simply, you will make it from here, and you will see it something like that. So you will find that our output is simply RC. Here, this is deactivated. So when you see the resistance from this side, it's very simple that R out equals RC. Now, let's start to determine the gain. How can we determine the gain? This is the input and this is the output. Let's now make it in the same way like we did in the previous example. Here we have an input and here we have an output. So let's start with the output. The output is very easy. This current is flowing in these two resistors, but in the negative direction. So V output equals to the current here multiplied by these two resistors, RC parallel with R out. So the first step we can say that V out equals to minus alpha IE multiplied by RC parallel to RL. Again, this current is flowing in these two resistors, but it's flowing from downward to upward to its negative direction of the voltage. So the voltage drop here is the current flowing, which is negative alpha IE multiplied by the parallel equivalent of the two resistors RC and RL. So this is the V out. Okay, then how can we link this with the input? Now we have IE. How can we link this IE to how we can link this IE to this branch? Okay, let's see it from this point of view. As I said, this is, let's call it VP. If you examine this branch, you can say that VP equals to the equivalent resistance here, which is R small e plus R capital E multiplied by the current IE. So let's write this equation. So VP equals to IE multiplied by R small e plus R capital E. That means that VP, or that means IE is equals to VP over RE plus RE. Now you can substitute in this equation and you can say that V out is equals to negative VP over RE plus RE multiplied by RC parallel with RL. Now it's a relation between V output and VP, but we need a relation between V output and V input, not V output and VP. So the next step is to link VP to V input. We did this in the previous example, if you remember. This is a potential divider. So VP, the voltage point, equals to this resistance, or first we equal to V swing times this equivalent, which is RB parallel with RE small plus RE capital over the summation of this resistance, which is RB parallel with RE small plus R capital E plus V plus R small. Again, let me make it in a better way. I believe you will not see it from this view. So let me replot it again. We have something like that. So this is V swing. This is R swing. This is RB. This is VP. And this is RE small. And this is RE capital. And this is ground. So the voltage drop here, VP, equals to V swing times. First, you have this equivalent, which is RB parallel to RE small plus RE capital. RB parallel to RE small plus RE capital over the summation of all resistance, which is R swing plus RB parallel with RE small plus RE capital. So now this is a relation between VP and V swing. So you can take this relation and substitute it here. Then you will have a relation between V swing and V out, which is the input and the out. So you can get the gain. So this is the overall gain. Again, the gain is negative. Now let's come to the final question, which is actually my first point. When we start solving this equation, I told you we don't need to make any DC analysis. Here you have to wait a bit and ask me why we don't need to make any DC analysis. As we can see here, this relation, for example, is function in the gain here, for example, is function with RE, for example. So we need to calculate RE. What about RE? Okay, RE, if you remember, I think I mentioned it in the beginning. I think I mentioned it somehow in the beginning. So yes, RE equals to alpha over GM. So alpha will be given because alpha equals to beta over beta plus 1. But what about GM? We need to make a DC analysis in order to calculate GM. How should we make it? Okay, let's wait. If you return to the lecture, you will find that GM is equals to IC over VT, where VT is the external voltage, which is typically 25.9 milli-electron volt, if you remember, or millivolt, sorry. If you remember that from the solid state course, this is the constant, at the constant pressure, of course. But what about IC? How can I calculate IC? Okay, let's wait. Now we have this current source. This current source is flowing here. So this current source, because now if we make a DC analysis, you know that this capacitor is an open circuit, so no current is passing here. So the current here in this current source will pass here. So this current I is simply IE, because this is the current flowing in the emitter. And as far as we are in the active, we can say that IE equals to IC over alpha. And you know alpha because you know beta. So you can calculate IC, which is a value you needed in this value, in order to calculate GM. So in order to calculate GM, what only you need is IC. You don't need to make a full DC analysis. And you will usually given this IC due to this current source. So as far as you have this current source, you don't need to make a full DC analysis for the circuit. You can calculate GM directly from this relation. Sometimes actually you can say that IE is approximately equal to IC when alpha is tends to 1. For example, if beta equal 200, then alpha will tends to 1, and then IE equal IC, and then you can get IC directly from this relation. So this is the end of our of this part, and actually this is the end of the lecture as well. Now we terminate the BJT lecture. Thank you for your concentration, and waiting for you in the last and in the final chapter, which is the operational amplifier chapter, starting from week 10. For 2 weeks, we will study what's called the operational amplifier. Thank you very much for your concentration.